7.3. Bit of a long one, but not a hard one. It's going to let us evaluate complicated things easily. So normally, if you had to actually calculate this Laplace transform using the definition, right? Let's remember what the definition is. Laplace transform of a function f is integral from 0 to infinity e to the negative st f of t dt, right? So whatever function you put in here, you have to integrate against e to the negative st. Again, would not be a fun time, but we can use some of these operational properties to see what e's and t's do to functions, right? That's kind of the idea. So it's going to turn out that e's are a shift operator, t's, correspond to taking derivatives. And then you can calculate the Laplace transform of sine. Wow, Okay, here's the first translation theorem. If you multiply, so if you have the Laplace transform of some function f is capital F of s, then multiplying by e to the alpha t shifts f from s to s minus alpha. Right, here's what it looks like in picture form. If this was your original function, right, when you take the Laplace transform of e to the alpha t times f, you just get this. You just shift by alpha units, right? We call this an s-axis shift, right? Translation along the s-axis. Here's an example. If you want to find the Laplace transform of e to the 5t times t cubed, what you can instead do is find the Laplace transform of t cubed and then shift that from s to s minus 5, right? So you do this Laplace transform, and then afterwards you take all the s's and replace them with an s minus 5, right? Because that's what alpha is 5 here. We know the Laplace transform of t to the n, right? Laplace transform of t to the nth power is n factorial over s to the n plus 1, right? So Laplace transform of t cubed is 3 factorial over s to the 4th, and then we shift from s to s minus 5. 3 factorial over s minus 5 to the 4th. That's it. That's the answer, right? So multiplying by e is a shift. Let's do it again. Laplace transform of e to the negative 2t cosine 4t. Well, we can find the Laplace transform of cosine and then shift from s to s plus 2, right, since alpha is negative 2. That means that s minus alpha equals s minus negative 2, which is s plus 2. So we calculate the Laplace transform of cosine 4t, right, which is s over s squared plus 4 squared. And then everywhere you see an s, you replace that with an s plus 2. S plus 2 over s plus 2 squared plus 16. This also works for inverse Laplace transforms, right? So we have this, right? We're going to notice that this denominator looks like something squared, right? Looks like s squared, but it's been shifted from s to s minus 3, right? So we're going to split the top, right? Split the top. Why did I use partial fractions? I don't remember. Oh, yeah. Whenever you have a squared in the bottom and a linear on top and you want to split it, it's best if we can have no s's on top, right? So to do that, we're going to partial fraction s minus 3 squared into s minus 3 plus s minus 3 squared. So hopefully we can get rid of all the s's on top. Okay, multiplying through by the denominator, right? We get 2s plus 5 equals as minus 3 plus b. 2s equals as, a equals 2, 5 equals negative 3a plus b, b equals 11, right? You just match coefficients here. It's pretty straightforward for this one. Okay. And that means the inverse Laplace transform of 2s plus 5 over s minus 3 squared is actually 2 times 1 over s minus 3 plus 11 times 1 over s minus 3 squared. Right, so this is the inverse Laplace transform of 1 over s, which has been shifted. Right, so when you're going backwards using the inverse Laplace transform, you can unshift, right? So it was 1 over s minus 3, but this is the same as 1 over s shifted from s to s minus 3. Same thing here, right? 1 over s minus 3 squared is 1 over s squared shifted. The inverse Laplace transform of 1 over s is just t. Oh, sorry, just 1. It's just the number 1. But this shift, right, the s minus 3 shift shows up in this e to the 3t. Same thing over here. The inverse Laplace transform, right, Laplace inverse of 1 over s squared is just t, right? But since there's a shift, that means there's an e to the 3t hanging out. Okay, let's keep going. Inverse Laplace transform s over 2 plus 5/3 over this quadratic, right? Let's notice that this guy does not factor, right? S squared plus 4s plus 6 does not factor over the real numbers. We've never seen this before, right? But if we can make it look like something squared plus something squared, that will be like a sine and cosine, right? So if we had like something involving s's squared plus some number squared, right? That would be like sines and cosines, right? So in order to do that, we're going to complete the square. If you've never seen completing the square before, it's really easy. You take half of b and you square it, right? That's 4. So half of b is 2. Square that, that's 4. Then you're going to add 4 and subtract 4, right here, right? Add 4, subtract 4. Now this becomes a perfect square, right? It'll always be s plus whatever half of b is, all squared, right? This will always be that. Pardon me. This will always be a perfect square of s plus b over 2. And then we have minus 4 plus 6 left over, right? So this is 2, and this is s plus 2 squared. Now, this looks like s plus 2 squared plus square root of 2 squared, right? Sines and cosines. Sines and cosines. So we do the thing. Excuse me. This is just replacing the denominators. The s over 2 and the 5/3 are hanging out. It looks like a shifted sine and cosine now. And to fix the top, we need to have some s plus 2's hanging around, right? There's a few ways to do this. I think there's a better way to do this later, but here's one way to do it, right? We've got 1/2 s plus 5/3. We need an s plus 2, so we're going to add a 1/2 times 2 and so take away a 1/2 times 2, right? So that way this becomes an s plus 2 times a half. Right, so we're compensating here, adding in what we need. So then we get 1/2 s plus 2 minus, this is 2 over 2 plus 5 over 3, and we get 4 over 6, which is 2/3. So we get 1/2 s plus 2 plus 2/3. And now we can split this up, right? We can split this up into two numerators, and one of them is a cosine. I think this one is a cosine, and this one is a sine. Right, so this becomes 1/2 s plus 2 over s plus 2 squared plus 2, and then we get 2/3, 2/3, and then we get 1 over s plus 2 squared plus 2. Now this looks like cosine, but it's been shifted, right? And if we unshift we get s over s squared plus 2. And same thing over here, if we unshift, we get 1 over s squared plus 2. Now this is cosine of root 2t. That's this. But the shift gives us this e to the negative 2t out front. Same thing over here. We need a root 2 on top. So we add 1 on top and divide out front by 1. That's where this comes from. Then this becomes sine root 2t, and the shift becomes e to the negative 2t. Okay? That's basically shifting, right? So let's solve this initial value problem, right? Y double prime minus 6y prime plus 9y equals t squared e to the 3t, such that y of 0 is 2 and y prime of 0 is 17. Now, we're going to solve this using Laplace transforms, right? So we're going to take Laplace transforms of both sides, right? Taking Laplace transforms of both sides gives us Laplace transform of y double prime minus 6 Laplace transform y plus 9 Laplace transform of y equals Laplace transform of t squared e to the 3t. Now, this, remember, when you take a Laplace transform of the nth derivative, right, you get s to the n you get s to the n Laplace transform of y, right? If you have the Laplace transform of y to the nth derivative, you get s to the n Laplace transform of y minus s to the n minus 1 y at 0 minus s to the n minus 2 y prime at 0, right? And you keep working down until you get s to the 0 y to the nth n minus first derivative at 0, right? That's the formula for derivatives. So we get s squared Laplace transform y minus sy of 0 minus y prime of 0. Same thing here, just a single derivative, right? One derivative gives me 1 power of s, and then I count down till I have no powers of s. And then this is just the Laplace transform of y. So these are the things we want to solve for. And then on this side, right, this is going to be Laplace transform of t squared shifted from s to s minus 3, right? And Laplace transform of t squared is 2 factorial over s cubed, shift from s to s minus 3. Now we plug in all the stuff we know. Y of 0 is 2, y prime of 0 is 17. So this is s squared, capital Y, minus 2s minus 17 minus 6s y of s. This is 2, right? This is 6. This becomes a plus 12. Plus 9y of s equals 2, which is 2 factorial, over s minus 3 cubed. And now we go to town, right? We just do algebra. So we're going to take these terms, these 3 terms, we're going to move them across, right? They become 2s plus 5. And then we're going to collect up our y of s terms. This becomes s squared minus 6s plus 9, y of s. A little word to the wise, leave these separated, okay? Try it. I wouldn't combine these if I were you, right? Okay, this is s minus 3 squared, right? S minus 3 squared. Now divide both sides by s minus 3 squared. We get y of s equals 2s plus 5 over s minus 3 squared plus 2 over s minus 3 to the 5th. And we need to split this up using partial fractions, right? So whenever you do, like if we were to have s minus 3 squared plus some number, then it would be a sine and cosine. and having an s up top would be okay. But since there's no number, this is a t. This is a t. This is a t to the, well, what is it? T to the first, right? Transform, technically. This is the Laplace transform of t. Some kind of that, right? So we need to not have any s's on top. So we need to do this partial fractional decomposition. And we've already done this. This is example number 3, right? If we go back. Right here, we did this partial fractions, right? So that means y of s is equal to 2 over s minus 3 plus 11 over s minus 3 squared. This guy doesn't have any s's on top and has a like an s to the nth term on bottom. So this is also a t to the 4th Laplace transform, right? This is some t to the 4th transform. So we can just leave it. Okay, so we pull the 2 off, pull the 11 off, pull the 2 off. 1 over s minus 3, 1 over s minus 3 squared, and 1 over s minus 3 to the 5th. Now, this becomes a 1, but it's been shifted from s to s minus 3, right? So it's actually e to the 3t times 1. This becomes a t, but it's been shifted, so we get an e to the 3t. And this becomes a t almost, it's almost a t to the 4th, but we need a 4 factorial, right? So we're going to add a 4 factorial on top and bottom. This one is going to become Laplace transform of e to the 3t times t to the 4th, right? And then the 1 over 4 factorial hangs out outside. That's it. That's it. Again, you can put the intermediate step if you want to, right? This is inverse Laplace transform of 4 factorial over s to the 5th shifted from s to s minus 3. And that's the solution to the DE, right? This is why. Solution to differential equation. Okay, next up, another differential equation, another initial value problem, actually. Take Laplace transforms. These are always super nice conditions to have, right? This is going to mean that the Laplace transform of like y to the nth power is simple, right? If you have this y of 0 is 0, y prime is 0 is 0, all that stuff, it makes it really nice. Okay, y double prime plus 4y prime plus 6y equals 1 plus e to the negative t. Take Laplace transforms everywhere. Laplace transform of y double prime, s squared, Laplace transform y minus sy of 0 minus y prime of 0. And again, both of these go to 0, right? Laplace transform of this is 4. Laplace transform of y prime, s, Laplace transform y minus y of 0, again, goes to 0. Plus 6, Laplace transform of y. Laplace transform of 1 is 1 over s. Laplace transform of e to the negative t is 1 over s plus 1. And for some reason I combine these. Yeah, I think it's fine to leave them combined. Sorry, to leave them separated if you want. You would just have to run partial fractions on this and this instead of just one term, which, you know, 6 of one, half a dozen of the other, honestly. Up to you. So divide by this on both sides after you combine the sides, or don't. And we get here 2s plus 1, s plus 1, and an irreducible quadratic, right? So we're going to run partial fractions to split this up, hopefully. Right, so we got a over s, b over s plus 1, and then a linear term over this irreducible quadratic. Okay. We've got, by multiplying through by the denominators, right, we'll cancel out these denominators. 2s plus 1 equals all of this stuff. You're just going to have to pick some convenient numbers, right? So pick some numbers. Hopefully you pick 0 and negative 1, and then you got to pick 2 more to get to get the rest of the coefficients. But then after you do all that, you get down to this point, basically, right? So this is just algebra. Right? So pick s equals 0, pick s equals negative 1, and then pick 2 others, maybe s equals 1 and s equals 2, I don't know, something like that. And then you get down to here. Now you can put the stuff in, right? We get 1/6 s, 1/3 s plus 1, and this looks familiar. We've seen this before in example number 4. Right? We've already taken that Laplace transform. You do it by completing the square on the bottom, right? Complete the square on the bottom, compensate up top. 1/6, 1 over s, 1/3, 1 over s plus 1, and then this splits into negative 1/2 s plus 2 over this, minus 2/3, right? Add the root 2 on the top and bottom, right? This was added. S squared plus 2 over plus 2. Sorry, this should be s plus 2 squared. Okay. Inverse Laplace transform of 1 over s is 1. Inverse Laplace transform of 1 over s plus 1. This is inverse Laplace transform of 1 over s shifted from s to s plus 1. So that gets an e to the negative t. Right, so this is 1 times e to the negative t. And then this we've seen already. This is cosine root 2. This is sine root 2. And the constants hang out. And that is the solution to the differential equation, which we could not have solved, most likely. Right? That's complicated. That's complicated. Okay? Next up, the other kind of shift, right? This is going to be an F shift, or sorry, a T shift. A T shift instead of an S shift. So the unit step function is defined to be u of t minus alpha is 0 for t less than alpha, and it's 1 afterwards. What this looks like graphically is from 0 to alpha, you're 0, and then you jump up to 1, and you carry on from there on. This helps us write piecewise functions, right, as products and sums of unit step functions. Here's an example. If f is equal to g between 0 and t minus alpha, between 0 and alpha, and then it's equal to some other function after alpha, then you can write f as g minus g times u plus h times u, right? So check out what happens here. Whenever t is on this interval, right, whenever t is on this interval, this is 0 and this is 0. So we just get g on this interval. And then after alpha, this becomes 1 and this becomes 1. And then g minus g leaves us with an h. So we're just h of t after alpha. You can also use it to define f that looks like this. So 0, g, 0. So we're non-zero on this alpha to beta interval, right? So what we can do is we can take f of t to be g of t times unit step function at alpha minus unit step function at beta. And you can check, right? On this interval, these are both 0. So the whole thing is 0. On this interval, this is 1 and this is 0. So the whole thing is g. And on this interval, this is 1 and this is 1. So the whole thing is 0. Here's an example. If f of t equals 20t from 0 to 5 and 0 after 5, then you can write f as 20t minus 20t unit step function at 5. Right, so on this interval, this is 0 and you get 20t, and on this interval, this is 1 and you get 0. Okay. Second translation theorem. If f of s is the Laplace transform of f, and alpha is some positive number, then the Laplace transform of f of t minus alpha times ut minus alpha is e to the negative alpha s f of s, right? So this is a t translation. Right, before the first translation theorem, right, was a s translation. Now multiplying by e to the negative alpha s gives you a t translation. Okay. Example time. If f of t is this, we want to find the Laplace transform of f of t, right? We've done this before with the definition, right? You can use the definition. If you like, you can use the definition. Okay, we're going to write this using unit step functions. So we get 2, right? And then it goes from 2 to minus 1, so that's a 3-unit drop, right? So that's minus 3 at t equals 2. And then you go up 1 unit, right? 1 unit up. That's a plus 1 u at t minus 3. Right, so this is t equals 1, t equals 2, t equals 3. Right? So you're 2, you start at 2, then you drop 3 units, then you rise 1 unit. Start at 2, drop 3, rise 1. Now we can take the Laplace transform, right? The Laplace transform of f is the Laplace transform of this side. Split it up, right? Okay, we've got 2 over s. Then this is f. This is f, right? So this becomes 2 over s minus 3, multiplying by u to the t minus 2 inside, right, gives you an e to the negative alpha s on the outside. So this becomes e to the negative 2s Laplace transform 1, e to the negative 3s Laplace transform 1. And then after we transform these, normally this would be, you shift the t's to t minus alpha, right? So the Laplace transform of 1 is just 1 over s. So this is the Laplace transform of this piecewise function, right? 2 over s minus 3, e to the negative 2 over s plus e to the negative 3 over ss. And it works inversely too, right? If you have the inverse Laplace transform of e to the negative alpha s f of s, that equals f of t minus alpha u of t minus alpha, right? So the inverse Laplace transform of 1 over s minus 4 e to the negative 2s, in this case alpha is 2, f is 1 over s minus 4, and Laplace inverse, the inverse Laplace transform of f is e to the minus 4, e to the 4t, excuse me. So when we take the inverse Laplace transform, right, this e shifts our f, right? So we go from f of t to f of t minus alpha, right? So instead of being 4t, it's 4t minus 2, right? This is t minus alpha. And then you multiply by u to the u of t minus 2. Here's another example. S over s squared plus 9 e to the negative pi s over 2, right? Alpha in this case is pi on 2. My capital F of s is this function. And the inverse Laplace transform of this is cosine 3t. So multiplying by e to the negative pi over 2s is going to shift this cosine, right, from t. So we're going to go from t to t minus pi over 2, right? So I get cosine, right? That's the inverse Laplace transform of this, but I shift from t to t minus pi over 2. And then I multiply by the unit step function at t minus pi over 2. And that's the Laplace transform of this function. Okay, this is useful. This is useful because a lot of times the right-hand side of our differential equation is a piecewise function, right? Is a piecewise function. So we got y prime plus y equals f, where f is this thing, and we're given some initial condition. So this is an initial value problem. We're going to use our knowledge to rewrite f, right? So we start at 0, and then after pi, this turns on, and we get 3 cosine t. Okay? Take Laplace transforms everywhere. We get Laplace transform of y prime plus Laplace transform of y plus f is this. So this Laplace transform of 3 cosine t ut minus pi. Okay? This is s y of s minus y of 0 plus y of s. Laplace transform of 3 cosine t times the unit step function. Complicated, but not too bad. The 3 comes out front, right? The unit step function tells us we get an e to the minus alpha s. And then we need to take the Laplace transform of cosine, but it's been shifted backwards, right? It's been shifted backwards to t plus pi. Right, and why does that happen? That happens because cosine of t plus pi is equal to cosine of t plus minus pi plus pi minus pi. Right? Well, okay. That was poorly worded. But the point is when you shift by negative pi now, right, you get back to be t. Okay, this side cleans up. This is a 5. So this comes across. We get an s plus 1, y of s. We get a 5 plus 3 e to the negative pi s plus transform of cosine, and cosine of pi, t plus pi is equal to negative cosine t. This is one of the properties of the trig functions, right? So then we divide by s plus 1 everywhere. Right, we're going to divide by s plus 1. Oh, sorry. First, we take the Laplace transform of cosine, negative cosine t, right? Negative s over s squared plus 1. Oops. Divide by s plus 1 everywhere, right? We get 5 over s plus 1. And then we get this over s plus 1. Partial fractions on this guy. Turns out that a is negative a half and b and c are 1/2. So now our problem looks like this. Y of s equals 5 over s plus 1 minus 3, and then this is the partial fractions, right? S plus 1, s squared plus 1, and then s squared plus 1. Right, because I split this up. So this is sines and cosines. And this is some t. Okay, we've got inverse Laplace transform of 5 over s plus 1 plus positive 3/2 inverse Laplace transform of s plus 1 over s plus 1 e to the negative pi s minus 3/2 inverse Laplace transform of s over s squared plus 1 e to the minus pi s minus 3/2 inverse Laplace transform of 1 over s squared plus 1 e to the negative pi over s. And now we're just going to do our thing, right? This is 5 over s shifted from s to s plus 1, right? So this is 1 times e to the negative t, 5 times 1 times e to the negative t, right? The 3/2 stays. This becomes e to the negative t, right? But we shift from t to t minus pi, right? But we shift from t to t minus pi. So this is inverse Laplace transform of 1 over s. Yep, that's right. So you get e to the negative t, but you change from t to t minus pi. And then you multiply by u to the t minus pi. Okay, that's how that works. Same thing here. This is just cosine t, right? Cosine t, but you shift from t to t minus pi. And then same thing here. This is sine. Well, almost sine. You need to... No, it is sine. It is sine. This is sine t, but then you go to sine of t minus pi when you multiply by e to the minus pi s. And multiply, obviously, by the unit step functions every time you translate. And then we can, if you want to, you can go back, right? So this is e to the 5t, and then after pi, these all turn on, right? So it goes from e to the negative 5t, and then it turns into e to the negative 5t plus this chunk, if you want. But this is fine. This is fine to leave it like this. Okay, a bit of application here. So we're going to have a beam. So consider the following setup. You got a beam of length L, which is embedded into the walls, right? And you've got variable load Wx applied to this beam, right? And we're going to say that the x-axis goes through the middle of the beam. In this case, the static deflection, y, right, on the beam is the solution to this differential equation, where this is Young's modulus of elasticity, and this is the moment of inertia of a cross-section of the beam. And then oftentimes Wx is a piecewise function, right? Because you'll have some box, right, sitting on the beam. So you'll have no weight in some area, weight, and then no weight. So this is actually a pretty nice spot to use Laplace transforms. So let's assume that the beam has length L and that we have this variable load Wx, which looks like this, right? So we can imagine what's happening here. The load is like a triangular piece of load, right? You've got a beam and you've got a triangular load sitting on top of the beam, right? And here it has some weight W naught, and then by the time you get here it has weight 0. And our goal is to find y of x, right? And we have a boundary value problem, believe it or not, right? Because we know that the beam is embedded in the wall at both ends. We know at zero, the position on the right-hand side of the beam, right? This point here is y equals 0, right? This is x equals 0, and this is x equals L. We know at x equals 0, the position of the beam is at 0 and it's not moving, it's not accelerating. And we know at L, it has position 0 and it's not moving. So these are our boundary value boundary conditions. And so we're going to note that we can write this piecewise function, right, as a sum of unit step functions. We're going to do a little trickery-dickery here because we need to get an x minus L over 2 in both spots, right? That makes the theorem a little easier to apply. So we're going to just factor this L out and this 2. So we get actually we're going to factor out negative 2 over L. Factor out that whole thing, right? Negative 2 over L. So we get an x minus L and an x minus L. Okay. Because when we take a Laplace transform of this, it'll look like this, right? This is f of x minus L over 2, which means it's like, yeah, okay, that makes sense. Yep. So we have this differential equation. We're going to take Laplace transforms of both sides, right? Laplace transform of this side is just EI, which are just some constants, and then we get the Laplace transform of y to the fourth derivative of y, and then over here we get the Laplace transform of w, which we've written conveniently, right? The fourth derivative of y, we get an s to the fourth y of s minus s cubed y of 0 minus s squared y prime of 0. These we don't know, right? We don't know y triple prime and y double prime is 0. So those are just going to have to hang out. We're going to call them some constants. And this equals, right, we're taking the Laplace transform of both sides, and this is w. So when we take the Laplace transform of this, not so bad, w naught 1 over s minus 2 over L 1 over s squared. And then the Laplace transform of this is w naught 2 over L, and this just becomes e to the negative alpha s times, excuse me, Laplace transform of this function without the x minus alpha, which is just 1 over s squared. So we get s to the fourth minus constant times s minus constant equals this horrible creature. Again, this is not too important to know. It's just important to see how you can use Laplace transforms, I think. Nothing this hard would be on the test, is what I mean to say. Okay, so we've got y of s equals this creature. Now we're going to take inverse Laplace transforms, right? Inverse Laplace transforms. Inverse Laplace transform. Inverse Laplace transform. Inverse Laplace transforms. Right, it's not pretty, but it's doable. Inverse Laplace transform of 2 factorial over s cubed is x squared. Inverse Laplace transform of 3 factorial over s to the fourth is x cubed. This hangs out. Inverse Laplace transform of this is x to the fourth, right? Inverse Laplace transform of this is x to the fifth. Inverse Laplace transform of this is, what do you get? You would get an x to the fifth, but we're shifting by L over 2, so it's really x minus L over 2 to the fifth times u x minus L over 2. To solve for the other two constants, you need to use the other two boundary conditions, right? And also, if x is bigger than L over 2, then this unit step function is just 1. Right, so plugging in y of L equals 0, we get 0 equals this, and you can solve that down to get this equation. Y prime of L equals 0. You have to take a derivative of y, right? Take a derivative of this. So y prime equals stuff. Again, this is way harder than anything you'll have on your test. C1x plus C2 stuff, and then you plug in 0 on this side and plug in L on this side, right? And you get this equation. And now solving this system, lots of algebra, okay, you get C1 equals this, C2 equals that, which means you can plug in for C1 and C2 and you have the solution to your differential equation. Wow. Okay, please do not focus on how awful example 12 was. It's just an example of how you can use Laplace transforms. Most of your homework and tests are going to focus on things that look like this, right? Things that look like this, things that are much easier than that, right? Things like example 6, right? These are much nicer, much more manageable things to handle. Okay, 7.3 done.